I want to welcome you to one of the Dean's seminar lectures. My name is Julio Utino. I'm the Dean of McCormick. I'm going to kind of stick to a script in here because this lecture is being broadcasted to another room where there is, I'm told, about 100 people as well. So it is my distinct pleasure to introduce Arun Majumdar, who is Vice President for Energy for Google. And he will be talking to us about energy and the industrial revolution, past, present, and future. So a couple of words about Arun. Not going to list everything that he has done. It will be way, way too long. But he drives energy initiatives at Google and advises the company on its broader energy strategy. In October 2009, he was nominated by President Barack Obama and confirmed by the Senate to become the founding director of the Advanced Research Projects Agency Energy, ARPA-E, where he served until June 2012. And between March 2011 and June 2012, Arun also served as the acting Undersecretary of Energy and a senior advisor to the Secretary of Energy. Prior to joining the Department of Energy, he was the Almy and Axe Maynard Chair Professor of Mechanical Engineering and Material Science at Berkeley, and the Associate Laboratory Director of Energy and Environment at Lawrence Berkeley National Lab. His research interests include the science and engineering of nanoscale materials and devices, as well as large engineered systems. He's a member of the National Academy of Engineering and a member of the American Academy of Arts and Sciences. And his degrees are from IIT Bombay and a PhD from the University of California, Berkeley. Finally, I want to thank the person who made this visit possible, and is Vinayak Dravid, who is sitting in there. So without Vinayak to orchestrate this visit, we wouldn't have Arun joining us today. And with those few words of introduction, I want to welcome Arun Majumdar here.
Thank you. Well, thank you, Dean Utino, for this very kind introduction. And I also want to thank Vinayak and his family for the really warm introduction and warm hospitality. And I've known Vinayak for years that if I tell how many years, they will reveal our age. But it's really always fun to come back out here in Northwestern. I've been here before, and usually I've given sort of scientific talks, and this one is going to be a little different. And since I'm at Google, I'm going to show only one slide from Google, but mostly from my experience in the Department of Energy, both as ARPA-E and the Undersecretary role. So I want to talk about energy and the Industrial Revolution. And I think what I'm going to do is, if you may, I'd like you to sort of step back and think about when the United States was being created, going back to the 1700s, the late 1700s, and what was life like out there. And normally we have only seen pictures, paintings. And typically you see a painting of George Washington, Thomas Jefferson, Declaration of Independence. And if you imagine what life was like, you see George Washington on his horse, the Revolutionary War, and people used to light their homes and buildings using lamps like that. And the fuel that was used for lighting at that time was whale oil. Oil from the ground had not been discovered yet. And that was, in fact, discovered during the Civil War. But if you go back to the 1700s, this is what life was like. And if you now fast forward for 240 odd years, and imagine now you know what the life is out here today. It has been the last 240 years of innovation. It's been a remarkable period in human history, and this is what we have today. And what we have gone, unfortunately, that's been cut off on top. We have gone from horsepower to horsepower. And so we go to our grocery stores today with 300 horses, 200, 300 horses taking us there, just for the small little trip. And I took the flight yesterday with 100,000 horses, bringing me here in a few hours, which would have taken anywhere from a month or more during the times of Washington and Jefferson. That's the transformation, and it has been one of the most remarkable periods in human history. And we light our homes and buildings like this, not with whale oil, but with electricity. Okay, this is, if you look at the whole human history of 10,000 and more years, the last 250 years has been very remarkable. So that's what we have today. And that has led to an immense amount of productivity as well as prosperity. If you look at the economic prosperity, the global per capita GDP has an exponential increase. And that has coincided, not accidentally, by the exponential increase in energy. So the Industrial Revolution is all about energy, how we use energy, going from horses and human power to real engines and mechanization. And if you look at the numbers, it's been mostly about 80% of that has been from fossil fuels. And in this period, there's another exponential increase, in fact, more than exponential increase that has happened, and that's been of the population. We had 700 million people at the beginning of the Industrial Revolution. We have 7 billion people, a 10x factor in a matter of 250 years. And if you look at the numbers going back to 7,000 BC, the population gradually, and you see the Black Death of the plague, little dip, and then you see that. That's been the population increase in the world. So in the big scheme of things, again, the last 250 years have been pretty remarkable. And the population by 2050, and some of the young people, the students, will still be alive at that time. It'll be 9 billion. 2 more billion will be added. And by 2100, it's going to be 10 billion or so. That's the estimation from United Nations. And really, that number really depends on the fertility of women in Africa. That's what it really depends on. So we're going to add about twice the population of China in the next 40 years. Okay? That's the reality. That's what we're going to face. The question is, if we want to keep this economic growth going, in the exponential increase going, do we have enough fuel to keep that economy going in the exponential increase? And of course, the question is, if the last 250 years has been about fossil fuels, do we have enough fossil fuels? So that's the question out here. Do we have enough fossil fuels to keep our population and economic growth going? The answer is absolutely yes. So if you have, this is now global oil reserves. They keep on increasing. This is global gas reserves without counting US shale. And what you find is that there is no peak oil, because the science and the technology for discovery and extraction of fossil fuel not only keeps pace with the demand, it's actually ahead of the pace. So now you find the gas prices going down a little bit, et cetera. So you find that there's a lot of hydrocarbons, almost the same amount of hydrocarbons as you have oxygen in the air. Tremendous amount of hydrocarbons that are there. And right now we're talking about shale oil and shale gas, and I'll say a little bit about that. But there's also methane hydrates that are there in the oceans, and we haven't even touched them yet. So there's a lot of fossil fuels. But if you are to go business as usual, there are a few things to remember in terms of what is business as usual. And you find out here the global oil price and the economic unpredictability. This is the oil price. This is a global price. Oftentimes, the president is said, the media talks about the president decides the oil price, and the oil price goes up, the president numbers goes down. And the president doesn't decide. It's a global market. And each of these fluctuations has huge impact on our infrastructure. And if you look at these ups and downs, almost all of them have been because of global events, not because of what's going on in the United States. So our future is not in our hands. It's decided by events that are outside the United States. That's what's going on. This unpredictability is a serious issue for economic security. And if you look at how much oil we use, you have the total US oil consumption on top. This is the percentage of imports, and our imports, this is the real numbers in terms of thousands of barrels per day. And you find that, yes, the imports are going down, and that's a good news. In fact, after a long time, the imports are less than the domestic production of petroleum. But yet, if you look at the amount of imports, we're paying about $300 billion a year, almost $1 billion a day. And think about the balance of payments. If you could use that money for economic growth out here, wouldn't that be much better than giving $300 billion to someone else? So that's we have to realize that there's an economic security issue. There's a potentially national security, not a potentially. This is a national security issue. And there's an environmental part which I'm going to talk about. But we are not alone in this. There are other countries in the same boat. So this is China. Their domestic consumption and domestic production, and you find they're in the same boat. So there are many countries, not just China, India, Germany, major economies, Japan in the world, who are in the same boat. We're trying to figure out how to get out of this. But they cannot, because they hooked on to oil. And then, of course, we know that if you use a fossil fuel, there is global warming. It's just the laws of physics that there will be global warming. And we know that the temperature rise so far has been 0.8 degrees since the beginning of the Industrial Revolution. The average temperature rise has been 0.8 degrees. But average is just part of the story. It's, in fact, is a smaller part of the story, because if you go on the streets of Chicago or Evanston and you say, okay, the temperature's gone up by 0.8 degrees in the last 250 years, most people will say, so what? My home, my bedroom changes by 10 degrees over a day. So it's not the average that is important. So I'm going to show you the distribution, the data on the distribution energy and how the distribution has moved. And I'm going to show you the numbers for summer temperature, the deviation from the average, normalized by standard deviation. So you'll see a Gaussian curve. And in fact, you will see first the theoretical. On the right-hand side, you'll see the red, which is hotter than average, and the colder than average. So let me just play this movie for you in terms of averages and extremes. Okay, so this is standard deviation, normalized. Now you see the data, 50s and 60s, 70s. It's sort of, the distribution stays about the same. And this is what happens. All right? So this is where the distribution is going. Clearly, the average has moved. There's no question about it. But that's just a small slice of the story. What is happening is that the distribution is broadening. And not only that, you're reaching temperatures which are 3 to 4 to 5 sigmas, 5 times the standard deviation of probabilities which were unheard of before. And that's what's going on. And these are what we call the heat waves. Last year, you had a massive heat wave in the Midwest. And a few years ago, it was in Moscow, where about 70,000 people died. Before that, it was in France and Europe, where people died. And that's what's going on. And if you look at the geographical distribution of these heat waves, clearly it's not cold waves. The distribution is not moving that way. It's moving this way. The direction is very clear. These hotspots are moving around every year. It's like a little bubble in the carpet, right? You press it out here, it comes up somewhere else. And so people normally, when they have short time spans or time horizons, they say, oh, last summer was really hot. This summer is not so bad. But if you look at it globally, there are these hotspots going around, and this ain't going away. Okay, so that's what's happening. So then you ask the question, let's put some numbers behind it. If you ask the question, what is the cumulative amount of CO2 that we emitted since the beginning of the Industrial Revolution? And it turns out the lifetime of CO2 molecules in the atmosphere is a few hundred years. Some of it goes in the oceans. It acidifies the ocean. But many of these molecules remain there. So it's really a capacitor. It's integrating all the CO2 that we emitted. So how much have we emitted since the beginning of the Industrial Revolution? And the number is about 1 trillion tons. And in fact, there was an IPCC report that just came out recently. It's about 1 trillion, roughly 1 trillion tons. Then you ask the question, based on the known fossil fuel reserves today, and just to note that these reserves keep on increasing because the technology improves, but today's known reserves of fuel, fossil fuel, down on the ground, if we take all that fossil fuel and decide to just burn it, okay, how much more CO2 can we emit based on today's known fossil fuel reserve? How much more CO2 can we emit based on fuel reserves? The number is about 3 trillion tons. So 3 times more CO2 is there, and this number will keep on increasing as the technology improves, right? So 3 times more. The first trillion took 250 years. How long do you think the $3 trillion tons of CO2 will take based on today's business as usual economic growth and today's use of fossil fuel? That number is shockingly 75 to 100 years. So 3 times more CO2 in about 1/3 the time. So you're almost a 10x factor. That's the world of the future if you do nothing. So then you ask the question, how much is this 3 trillion tons of CO carbon really worth? What's the dollar value? And that number is about tens of trillions of dollars, roughly $30 trillion or so. And this is what society is often given the option, a choice. Do we keep those $10 trillion in the ground and do not use it for economic growth, but we save the environment? Or do we take those $10 trillion and have this exponential growth to hell with the environment? That's the choice that is given. And that, my friends, is a false choice because it does not take into account the ability to innovate around it. And it is best articulated by the former oil minister in Saudi Arabia. The Stone Age did not end because we ran out of stones. It's because we transitioned to better solutions. And my former boss, Steve Chu, and I wrote a paper that came out in Nature calling for a new industrial revolution that is sustainable, and gave a snapshot of what that revolution might be looking like. And I'm going to give you a few ideas that we proposed out there. And this is where I show my first slide, or just one slide of Google. What are we doing in Google? We have 100%, I'm sorry it's clipping off out there, we're 100% carbon neutral company in Google, 100%. And how do we get there? There are 3 ways. One is that we make our big computers, we have the largest computers, big computers as efficient as possible. So energy efficiency, why? Because it saves us money, frankly. So that's number 1. Number 2, we invest in renewable energy. We have invested about $1 billion, mostly in the United States, now we're going globally, in renewable energy projects, whether wind or solar, et cetera. We just announced one in South Africa, large solar farm. And we have done that across the United States. $1 billion in project finance. And finally, what we cannot do, we offset. We pay more. In fact, we have introduced something called green tariffs in North Carolina because we have data center in North Carolina. We will pay a different rate for electricity if it is renewable than if it is not. So we're willing to do that because it comes right from the top. So that's what's going on in Google. But I'm going to share with you some of my experiences that I got to see from RPE, that we transitioned to better solutions, what those solutions could be. So just to give you an idea of what RPE is like, how was it created and why was it created? What was the mission? In the area of energy, there are 2 things that are really important. One is cost, and the other is scale over time. The scale is the amount. If a technology doesn't reduce in cost and doesn't scale up in volume, it doesn't matter. So all technologies follow what is called a learning curve. So this is now a horse carriage car, which, this is existing. Think about now the early 1900s, where this was the prevalent technology, existing technology. Now you could make this better and better. You could make better wheels, better wheel bearings, stronger horses, and you could keep going down this learning curve. Whereas at that time, there were a few crazy ideas or perhaps this could be disruptive, transformative and disruptive. And those were the ideas. They were steam-powered cars. They were the Benz motor wagon. And all of these, there were multiple shots at goal. Each of them would be transformative if they had succeeded. But out of all of those, one of them succeeded. That was Model T. Oh, sorry, yeah, Ford Model T. And that became disruptive because it was just better. It was cheaper over a longer term. And it was environmentally much better because you did not have to deal with horse poop in your streets. And this was a big deal. This was a huge environmental, because there were guys who were really digging out all the stuff from New York City and all that. And this was just cleaner. So it was cheaper, better, and cleaner. And that was a disruptive. It was not only transformative, but it was disruptive at the same time. So ARPA-E's goal was to do this to today's energy technology, to be transformative and disruptive solution in the energy sector, so that it would ensure energy and environmental security, as well as provide the US with the technological lead. So that was the purpose. Now, talking about energy, it's very important to understand the whole system view. And this is where engineers come in, to take a system view of things. And what is the system view? Well, in the energy system, there are two systems. One is the stationary power system. The other is the transportation system. And stationary power is electricity, natural gas to our homes, et cetera. And the other is transportation, which is gasoline-based, mostly gasoline and diesel, and that's the transportation. And these two systems really don't talk to each other. They're independent, except for the introduction now of a very small amount of electric vehicles. Otherwise, these systems don't talk to each other. So I'm going to talk about these two systems, but perhaps what I'm going to start with is what has been perhaps the most disruptive thing that has happened in the US energy industry, and that is natural gas. So this has happened because of horizontal drilling and hydraulic fracturing. For those of you who are not familiar with this, this is how it is done. You drill about 8,000 feet, 7,000 to 8,000 feet, to the shale region out here, and then you drill vertically, and when you reach the shale, you go horizontally. And this shale is extremely impermeable, so you got to fracture it to increase the permeability, and you get shale gas. Now, it turns out that this research has been going on, funded by the Department of Energy, since the early 80s. And at that time, this was thought to be one of those crazy ideas, potentially transformational, but it was too expensive. And over the years, they brought the cost down to the point that about 5 years ago, it became cost effective. And then it was a massive boom. It became disruptive. But while there's a tremendous amount of euphoria, and understandably so, because of shale gas and shale oil, one has to look at the numbers. And I'm going to give you, and I'll give you the science and the engineering aspect to it. There's a coupling of chemistry, transport, and mechanics, which is very complex. And there's a lot of room for science and engineering to go there. I'm showing you the picture of the flow rate of these wells. And if you look at the first wells that were dug in before 2005, these wells peaked, and then after the peak, it went down. And over the years, we've become better and better in extracting more flow rate out of these, and so the peaks are going up. But there's a big tail of the distribution, and while we are all euphoric about the amount of abundance of natural gas, no one talks about the error bar. Because the error bar depends on this tail of this distribution, and we really don't know when this tail will end and what shape it will be in. Because we really don't understand the science and the engineering. Why don't we understand? Because it is a coupling of the chemistry, transport, and mechanics. This is what a shale rock looks like. If you do an electron microscopy, you'll find that the inorganic material is coated with an organic material called kerogen, very long chain hydrocarbons. And in those kerogens are these pores. And these pores is where the natural gas or the long chain hydrocarbons are adsorbed, or physisorbed on this material. And they follow Langmuir isotherms. So these pores out here have this coating, and the expansion of these pores, the permeability of the pores, depends on the pressure. So the fluid mechanics and the solid mechanics are coupled. But in today's transport, today's modeling of the shale, the models, the simulation, the computation models don't have that coupling. That's the state of the art. And these pores are so small, they're on the order of 10 to 100 nanometers. The transport of these gases, in some cases, follows Knudsen flows. It's not viscous flow because the molecules are bouncing off the walls. And so we don't know whether this tail is due to diffusion or desorption, the chemistry and the transport, or whether this is Knudsen flow. We don't know. And so this is the state of the art today. Nevertheless, this has been very disruptive in a positive way because what it has done, purely because of economic reasons, it has become the cheapest way to produce electricity and is displacing coal, which is much more carbon intensive, purely because of economics. So if you look at the electricity production, this is the levelized cost of electricity generation. There's a red bar I put out there of 5 cents a kilowatt hour. Why? Because that is roughly the cost of electricity production from natural gas using what are called combined cycle turbines. The two cycles, one is a Brayton cycle, the other is a Rankine cycle, and it uses the waste heat to produce more energy. And these turbines now that are made by GE and Alstom and Siemens and others, they're more than 60% efficient, which is amazing. And they ramp up at 50 megawatts a minute. This is, they don't not only provide baseload power, they can ramp up and firm wind, intermittent sources, wind, et cetera. So these are natural gas combined cycle. The low cost of natural gas feedstock, as well as the high efficient turbine, makes it the cheapest, and that sets the bar for every other electricity generation scheme. The question is, where are the rest? So this is where the production is. If you look at nuclear is more expensive. Certainly all of them are more expensive. Wind actually is cheaper than coal in many parts of the country. It's about 7 or 8 cents a kilowatt hour. Solar, right now, it's about 10 to 15 cents or 18 cents a kilowatt hour. And DOE, we created a SunShot Initiative, that just like President Kennedy had the Moonshot Initiative to go to the moon and return safely within a decade. The SunShot was not, this for President Obama now. The SunShot was not to go to the sun and return safely. That would be pretty hard. But to reduce the cost of electricity, the unsubsidized cost of electricity of solar, down to 5 cents a kilowatt hour within this decade. And if you could do that, that's a big deal. And so that was the initiative. And let me just show you that there's a very big difference, by the way, in these kinds of electricity generation versus that. This is centralized base load generation in gigawatt scale plants, whereas those are distributed and modular, and that has a major impact on the grid. So what is happening in wind? Well, this is what is going on. You have the cost of electricity production from wind, which used to be in the 1980s at 55 cents a kilowatt hour, down there below 10 cents a kilowatt hour today, and the deployment, installed wind capacity in gigawatts has gone up. This is still 50 gigawatts or so. And the US electricity capacity is a terawatt. So we have a long way to go. But nevertheless, this exponential, there's a trend that we can see out here. So while this is going on, I wanted to highlight some challenges in these industries. What's going on? What are the materials issues? In this, one of the major material issue is that in these wind generators, the magnets that are used are based on rare earth materials. So these are iron boride magnets with a little bit of neodymium and dysprosium, and 95% of the supply of rare earths come from China. And they have internal demand out there, which means the supply, there's a risk associated with that. So we created a program on trying to look for magnets, permanent magnets, which are without rare earths. And there are many phases of materials that were being probed and investigated before iron boride magnets came along, but they were ignored because iron boride and neodymium-based magnets took over. And this is one of them. This is iron 16 nitrogen to iron nitride magnets, which has a huge crystalline isotropy. And they have been shown in thin films in terms of, and the energy density is actually better than the iron boride-based magnets, but they had never been shown in bulk material. Thin films are great. It's good for data storage, but not for permanent magnets for changing mechanical to electrical energy. So there are 3 groups out there. There are many other approaches to this. I just wanted to highlight one approach. And this is a major technological issue. Let's talk about solar. This is the panel cost, in terms of dollars per watt. And today, the cost is less than $1 per watt. In fact, if you look at the panels that we get from China, it's anywhere from 60 to 70 cents a watt. And that's really cheap. But the full cost is not the panel. In fact, majority of the cost, the fully installed cost at the utility scale in terms of dollars per watt today is about $2.50 or so, slightly more than $2. At the fully installed residential, it's about $3 to $4 a watt. So this is the panel cost, and that's the rest of what is called the balance of system. So that is installation, permitting, all kinds of things. And some of the money you got to pay to the utilities. All of that cost is higher than the panel cost. So you can give the panel for free, and you still won't get 5 cents a kilowatt hour. The question is, while we can improve the permitting, and that depends on local government procedures, et cetera, what are the technological knobs out there to reduce the balance of system costs so that you can hit the 5 cents a kilowatt hour? There are two knobs out here. One is the weight. If you can make it lightweight, you can go thin film. The other is the efficiency. Because if you increase the efficiency, you need less panel to install to produce the same amount of power. So this is now if you look at the efficiency, there is a red bar is the single junction theoretical limit called the Shockley-Quasar limit. So the question is, how far are we for the limit? For crystalline silicon, the production level is about 24%, 23, 24%. And it's a very tight tolerance, sun power, et cetera, based on that. So there's a little bit of headroom, but it's getting there. On the other hand, if you look at multicrystalline silicon, SIGs, and cadmium telluride, these are the different materials of solar panels, the production level is anywhere from 13 to 15%. And so but the theoretical limit is still the Shockley-Quasar limit. So there's plenty of room at the top. And that's where the material science needs to go to really understand what is a dislocation density, how do you get rid of them, how do you control the interfaces so that at the production level, not just in the lab, the production level, the efficiency can be raised to about 20%. Because if the efficiency goes to 20%, it's a game-changing technology. Because then you can reduce it down to about 5 cents a kilowatt hour, the levelized cost of electricity. Just to say that this is not the end of it, this is now gallium arsenide or 3,5 based devices coming from Alta Devices, Harry Atwater and Eli Jablonovich's company, that are producing 28.8% in the lab. Okay, this is 3,5 on plastic. They've been able to transfer this 3,5 single crystal material onto plastic, and now they're getting to production. If you can even produce 25% at production level, that's amazing. And then they can go from single junction to multi-junction at 60 cents a watt, it would be phenomenal. That's the direction, that's where the material science really needs to go to see how to increase the efficiency of this cell. Now for renewable electricity, of course these are intermittent, and while you can integrate to some extent on the grid, today it's about the wind and solar, mostly wind, is about 3.5% on our grid today. But if you get to about 10 or 15%, we really don't know, more than 15%, we really don't know how to integrate that onto a grid while keeping the frequency at 60 hertz within a very tight tolerance. It's very hard to do that. Our dispatch models on a grid don't quite exist in real-time markets. So we need storage. So storage, again, is a cost issue, cost and scale. How do we scale to gigawatt hour scale so that the first cost, the capital expenditure, is less than $100 a kilowatt hour? Why $100 a kilowatt hour? Because the existing technology, pumped hydro, is at about $100 a kilowatt hour. Whereas all the battery technologies, the flow batteries, et cetera, used to be about $1,000 a kilowatt hour or about $500 to $700 a kilowatt hour. So we created a program in grid scale storage saying that you got to get to $100 a kilowatt hour capital expenditure and have round trip efficiencies about 80% or so and last about 5,000 cycles, because then it really matters. That would be a winning technology. And that led to multiple approaches. I'll show you a few. So the idea was, how do you get those things down to $100 a kilowatt hour? This came out of City College, New York, or zinc manganese oxide batteries. These are not flow batteries, but they've done some beautiful combination of fluid mechanics and chemistry to prevent dendrites from growing, et cetera. And they're getting to about 2,500 cycles. Current cost is $300 a kilowatt hour. They're trying to get to $100 a kilowatt hour. The competition is on because they're not the only ones. This is coming out of Arizona State, Fluidic Energy, or rechargeable zinc air batteries. This is coming from Yetmin Chang's group, a whole completely different architecture of a flow battery using the best of the lithium-ion chemistry in conducting polymer fluids. And then, of course, zinc-based battery, Primus power. So this is just a few examples. There's a whole competition that is going on right now. But this all has to be integrated on the grid. So let me spend a few minutes on the grid. Grid, the electricity grid is it's been claimed to be the greatest engineering achievement of the 20th century by the National Academy of Engineering. But here's something that few people forget. The architecture of the grid, the paradigm that we live in, you've got centralized generation away from population centers, and to transmit the electricity, you've got to go up in voltage, okay, to about several hundred kilovolts, go long distance, and then to load centers where the cities are, you've got to go down to the distribution level voltages and distribute your feeder lines in your homes or the residences, the feeder lines about 13 kilovolts, and then you get 240 volts out to your home, out of which you use 120 volts. That's what we do today. That paradigm goes back to Tesla and Edison. And this is the paradigm we're talking about. It's a one-way centralized generation. Why centralized? Because it was cheaper. And a one-way powerful distributed load, that architecture goes back to Tesla and Edison, Westinghouse, and GE. And that architecture has not changed. And today, in that architecture that we use today, we have $100 billion per year of losses because of outages. And the average outage is amazing. It's about 1.5 hours per year. It may seem that's the average, but if you look at the extremes, it's absolutely amazing. What happened in Sandy, there were hundreds of thousands of people who lost power, and after 2 weeks, about 50,000 people still did not have power. And those, by the way, the amount of losses because of weather-related events, it just keeps on going up. You look at the data, it just keeps going up. So this is a major issue. And if that's the issue, I'm going to bring out another issue in our grid today, which is cyber-physical security. And I call it cyber-physical because it's not just cyber. And I'm going to share with you one incident that happened in pretty close to where we live. This is, some of you may know this, if you go on Highway 101 between San Jose and if you go towards Almaden, towards Morgan Hill, you might recognize next time there's a big substation where all the transmission lines come, and then they go down in voltage, and then the power is distributed to San Jose. And so this is, it's very visible. And on April 16th of this year, 2013, at 2 a.m., the people with guns came, and they probably had thermal cameras, because there were 120 shots fired. They knew exactly where to fire the radiators of only the energized transformers, which are hotter. And they shot those bullets right at the radiators because these transformers are cooled by mineral oil. So they leaked 50,000 gallons of mineral oil and tripped all these transformers. But what is interesting is that 15 minutes before that, the same people would probably cut the fiber optic and telephone line so that 911 was disabled. Talk about cyber-physical. And no one heard about it. And we wondered, we live pretty close by to this. We didn't hear about this. You know why? Because it was less than 24 hours after the Boston Marathon bombing. So while the whole media, everyone was focused on the Boston Marathon bombing, and they were doing all this in San Jose, on the other end of the country. And this is, we still don't know who did it. The Homeland Security, I'm hoping, I'm praying that they're looking into this. But that's the vulnerability that we have in our grid today. So what have we done in our grid? How have we modernized from the Tesla Edison state to now? What we have done today in what is called the smart grid, we have done only measurement. We have set up the measurement system. These are what are called phasor measurement units. We have about 1,000 phasor measurement units. These measure the voltage, the current. These are on the transmission system. The voltage, the current, the phase angle, the frequency, and the geographical location, because GPS, and timestamp. And now we're getting every 30 milliseconds from these 1,000 sensors out there in the transmission network, we're getting data every 30 milliseconds. So now we have petascales of data and we don't know what to do with it. And so this is where computer science comes in. We have big data, and the idea is to get situational awareness of this from this data. So this is what we really need to do, extract useful information out of the petascale data. And now I've gotten Google, the big query guys, the big data guys, to get interested to help out the ISOs and the utilities to look at data and make some sense out of it, to get situational awareness, to be able to manipulate things. We don't even have real-time markets. Most of the electricity that is coming today was planned out yesterday. Most of the electricity, it's a day-ahead market. We don't have real-time. Well, maybe with the data, we can do real-time market with real-time control, not only of the demand response, but the supply response. The demand and the supply, they don't talk to each other today. That's the state of affairs. So I think there's a lot that can be done. And what would be really useful, not only at the system level to be able to route power, we don't route power today like we route data. Power flows just like water down a hill on a transmission network. So if one line trips, the power goes somewhere else, and then you have a cascading failure, which is what happened in 2003 blackout in New York, the Northeast, and the 2011 blackout in San Diego. That's the state of affairs. We don't know how to route power yet. So when we were in the DOE and ARPA-E, we focused on one of the technologies that is absolutely critical for this, and that I'm hoping all the engineering schools and colleges really pay attention to. This is power electronics. And power electronics is doing the same voltage conversion and AC to DC, DC to AC, not by transformers and magnets and coils, but by electronic means, by switching using power transistors. The switches, in this case, we have to go to wide bandgap because silicon is not enough. And wide bandgap, why? Because we can go up in frequency. Why go up in frequency? Because the inductor size, because all these circuits have switches, inductors, and capacitors. Because inductors and capacitors can look at the high frequency noise and filter them out. So we need filters. So those sizes depend on the frequency. If you go up in frequency to hundreds of kilohertz as opposed to 60 hertz, the inductor size can go down, and that's cost. So cost goes down. And if the frequency goes up, the capacitor size goes down. That also is cost and reliability. So there's a big system level optimization that can be done if you had the right switches and the right magnets and the right capacitors. This is a materials problem, a system level design circuit topology problem as well. Just to give you one example, why is this important now? Because if you look at the substation transformers that I just showed you, each of them is about 8,000 pounds. They run at 60 hertz, and you need a crane to install it. And the average age of transformers in the United States is 42 years. And the expected lifespan is 40 years. So we are 2 years beyond the lifespan. That's the average. And we're living on borrowed time. And the backlog for these transformers is anywhere from 6 to 24 months. So there's stockpiling going on. By the way, we don't only do nuclear stockpiling. There's transformer stockpiling going on because we don't have reliability in the supply of these transformers. So we said maybe we could do better. And so I'm going to show you one example. This is the heart of a converter, is the transistor. This is a silicon carbide IGBT, a transistor, a power transistor, which can drop 15 kilovolts across a 200 micron thick layer of silicon carbide. So this has to be dislocation free, otherwise you got resistance, you got latch up problems, etc. And it can run 100 amps. So this is 1.5 megawatts of power. Okay, switching, not at 60 hertz, but 50 kilohertz. This is equivalent to running 200 homes, the power going through a transistor. Now you take these transistors, put them in a circuit, which are 4 or 6 of them, depending on the number of phases you have, and now you can do power conversion. And if this is possible, and they have actually shown it, this is Cree, then that 8,000 pound becomes smaller, because inductors and capacitors are smaller, they can fit into 100 pounds. That's the estimate. And that's the disruptive innovation that could potentially happen if you do the right kind of engineering. But this needs magnets. Now, not hard magnets now, but soft magnets. And as you know, as you increase the frequency in a magnet, the losses go up, both because of domain wall movement as well as eddy currents. So how do you design soft magnets in which the federal government had never invested in before because of We went on hard magnets because of data storage. Soft magnets are very important for power so that you can reduce the conductivity of these materials. And if you can get single domain walls, the losses go down. And so there's a huge effort. By the way, this is now the biggest challenge. It's not so much the switches. We can get gallium nitride and silicon carbide switches, but the biggest problem is to integrate the magnets in the right way. Let me talk very quickly about transportation. Today, transportation is predominantly due to this combined system, gasoline or diesel and IC engine. Now, there is a little bit of natural gas that is going on in the trucking industry. LNG-based trucking is shifting over to LNG because it's just economical. And there's an infrastructure that's been created across the United States. The other source of energy could be biofuel. I'll talk a little bit about that, but electricity, which is where electric vehicles are coming in. And at the end of the day is the battery cost. And this is the trend of battery cost that is happening. And you find that it is the battery cost has gone down by a factor of 2 in the last 5 years or so, which is pretty phenomenal given the history of batteries, which is more than 100 years old. Okay, so this is happening, and the uptake of EVs is going up. But this is not the end of the story. In RPE, we said that how can we make electric vehicles have a range and cost that is comparable to gasoline-based cars without subsidies? Because that's sustainable business there. And clearly, lithium-ion is while it is important, is not enough. So this is the energy density in watt-hour per kilogram of lead acid, of nickel metal hydride, and lithium-ion batteries. And this is what it's today. It's about $500 a kilowatt hour. And our goal was to go beyond lithium-ion to reduce the cost to $250 or less per kilowatt hour. But this is the batteries for electrical energy storage for transportation. That's the BEAST acronym, to go beyond that. And what else is there? There are lots of magnesium ion, advanced lithium ion, lithium sulfur, lithium air. These have been tried out before. This is not the first time. But the federal government had forgotten to invest in them for a long time. We said, we have to look at these because, yes, these are hard problems. The electrode, we don't know all the side reactions. We haven't invested in electrolytes. But you got to invest in them to be able to make some progress. I'll show you one example which has shown 400 watt-hours per kilogram. There are lots of engineering issues still remaining. And this has to do with Argonne National Lab. This is the NVIA battery, where this is licensed from Argonne National Lab, the cathode. In this case, in these layered materials, which have a much higher energy density, much higher stability. But on the anode side, it's not using graphite but silicon. This is a major engineering issue because when lithium goes into silicon, it just distorts the whole lattice. And it just makes it amorphous. There's a mechanical aspect to it. There are all kinds of side reactions that go on with the electrolyte and silicon, and lithium gets consumed. And the number of cycles is just not enough. So it really needs research to find out what the heck is going on in there. So if you could do this properly, and if you can get to about 1,000 cycles at 400 watts per kilogram, and at the cost, which is $250 a kilowatt hour, this is a game changer now. Now you're talking in terms of comparable range and cost. Finally, let me say a little bit about fuels. Sunlight to Fuels, I know you have an institute out here. And I want to say a few things of what's going on in the whole field. Most of the biofuels that have been worked on are photosynthetic biofuels. And these are all either based on switchgrass or cellulosic biofuels or cane or algae or corn based. And whether you get ethanol, whether you get pyrolysis oil or biodiesel, these are all based on photosynthesis. And photosynthesis by its very nature is based on what is called the Calvin-Benson cycle. And the Calvin-Benson cycle is very inefficient. The conversion efficiency from photons to oil, chemical bonds, is less than 1%, which is why you need a lot of land and a lot of water. And the feedstock cost, predominant cost, is collecting the feedstock and concentrating it. That's the majority of the cost. And so this is what is going on. And of course, there's a DOE had a lot of investment in that in terms of JBay, which is the Joint Bioenergy Institute, which is the precursor for the hubs, Energy Sciences Institute from BP, the Biomass Program, and DARPA had invested in all of this. And so the research needs to go on to reduce the cost, because you really got to compete with fossil fuel or based oil. There's a non-photosynthetic route as well. And these could be up to 90% efficient. And what had been done is catalysis. If you have syngas, you can use Fischer-Tropsch ways to make oil. And you can, or you can do artificial photosynthesis, which is the Joint Center for Artificial Photosynthesis based in Caltech and LBL and Stanford, et cetera. And that's going on. And we really don't understand completely how photosynthesis works. So that's the other chemical catalysis. What we started in ARP-E is something called the biological catalysis, which is electrofuels. And what is this? This is using non-photosynthetic microbes. And the idea is to generalize the concept of photosynthesis by not just using photons, by using any reducing equivalent, whether it is hydrogen sulfide or hydrogen or oxidizing iron from +2 to +3. These are microbes. Some of them live in the deep down ocean vents. There is no sunlight out there, but they still survive. They still make carbon-carbon bonds. And the way they do that is to get energy from any of these reducing equivalents. And then not use Calvin-Benson cycle, but many other cycles, which are much more efficient in making carbon-carbon bonds. And then if you can get to molecule like acetyl-CoA, you can go into biofuels, or you can go into bioproducts. And this route had not been explored in the past. And we said, let's go into this because the efficiency is much higher. And sure enough, in a couple of years, this is just one example. There are 3 other examples. This is the first biofuel without the use of sunlight. And this was 2 years ago. Last year, these guys showed that you can make a flask, and hopefully they will succeed in making reactors which will scale in cost and volume. There's another one which is kind of amusing. We create another program. So can we engineer plants not to produce cellulose, but to produce oil directly? Oil directly. And I'll just show you one example, and at cost, and at energy density. And I'll show you one example. And that is, we all know algae can produce oil, but algae has other problems. It has cost because of the reactors, it has infections, and the algae can go bad, et cetera. But what is really important in algae is the metabolic pathway that makes oil. So this group at LBL said that, why don't we take just the metabolic pathway in algae and insert that into a plant that grows in bad soil called tobacco. And we know a lot about tobacco, the engineering of tobacco. So they said, why don't we take that and put that in tobacco? The idea is that if you just take these leaves and just squeeze them, oil comes out. And I hope they are wildly successful, because then you would have big oil and big tobacco come together and save the world. Right? You can't get better than this. And what I've heard recently is the following, that they've actually succeeded in doing so in the lab, which is absolutely spectacular. So what I'm going to end with the following, and this is a very engineer's look at what is sustainable growth in the 21st century. And this is my personal viewpoint. It's a very engineering input-output kind of system. If you look at this, what's going on is the following. We have growth. We have population growth that's going to happen. We're going to add 3 more billion people in the 21st century. And we want the economies to grow. We don't want the economies to go down. So this system, think of it as a black box. And this is growing. And for it to grow, you need some input. And the input is the following. You need energy, you need food, you need water, you need material resources. And sometimes we have access constraints on the axis, which is what we call national security, et cetera. Okay? So that's on the input side. On the output side, well, this produces waste. There's emissions and waste. And that's the output. And now we know that output cannot be unconstrained. So this is the environmental problems and all that. So people either focus on the national security or the environment problem, but frankly, it's looking at the same beast in different angles. And what no one has figured out, which is I think the challenge of the 21st century, is how to close the loop in an affordable way and at scale. And we haven't quite figured this out yet. And frankly, you may say, oh, this violates the second law of thermodynamics. How can you do that? Because CO2 has a much lower free energy state than the hydrocarbons. True. So you need some energy. But the energy cannot be part of the system of producing waste, because then you haven't really solved the problem. And so that's why you need some emission-free energy that is affordable and accessible around the world. And that has to be carbon-free, solar, wind, et cetera. If you could use the energy to close this loop, then we have a sustainable growth model for the 21st century. And right now, we don't have that. And a lot of people say this is impossible to do. Well, let me show you a few historical examples of what people said was impossible, what people did not anticipate, the disruptive innovations that can happen, which is where research goes in. These are infamous predictions from the past. This is Sir William Preece, the chief engineer in the past. The Americans have need of the telephone, but we do not. We have plenty of messenger boys, and sort of missed the whole idea of telegraphs and others and the telephone system. But he was not the only one. This is another infamous prediction by a scientist. This is Lord Kelvin in the 1890s. Radio has no future. X-rays will prove to be a hoax, and heavier than air flying machines are impossible. He was opinionated, but he was wrong. And he was not the only one. He seemed to have managed to convince Wilbur Wright, who said in 1901, man will not fly for 50 years. Thankfully, he did not take himself too seriously. But I think it's the best way to articulate what could be in the future is what Arthur C. Clarke said. Any sufficiently advanced technology is indistinguishable from magic. And I think it's really for us scientists and engineers to do some magic now and to prove, not without violating the laws of science, to prove this can be done. Thank you very much.